Good morning students. In the previous class we have solved one problem under direct decomposition method where the matrix A, B is directly given in the problem. Now we will see one more problem whose matrix is not given. Instead of that they had given one transfer function, that is y of s by u of s is equal to 10 divided by s plus 1 into s plus 2. In this we will identify here also consider the linear system described by the transfer function. Design a feedback controller with a state feedback so that the closed loop poles are placed at. So here also they had given 3 poles. The first pole is going to be lambda 1 is going to be minus 2, lambda 2 is going to be minus 1 plus j1 and lambda 3 is going to be minus 1 minus j1. So here they have given 3 poles. Before getting into the problem, before you identify the state feedback gain, first identify whether the system is completely controllable or not. To find the system controllability, here as Kalman's test is very easy to identify the system controllability. Here also I am going to prefer the Kalman's test, since when you multiply the denominator, here a matrix AB is not given. So from this transfer function I need to identify what is my A and B. For that we can identify y of s is equal to 10 divided by s cube plus 2s square plus s square plus 2s. When you multiply s into s plus 1 into s plus 2, you are going to get this particular term. So after simplifying, you will get y of s is equal to y of s by u of s is equal to 10 divided by s cube plus 3s square plus 2s. Then I have to identify my matrix AB. I have to identify. For that I need to solve by any one of the method, either by using a phase variable method or by means of your partial fraction method or by means of your direct decomposition method. So all these methods we have done in our first module. So using any one of the method we have to identify the matrix A and B. Here I am going to prefer at phase variable method. So in phase variable method the system variable is going to be my first variable. So here y of s by u of s is equal to 10 divided by s cube plus 3s square plus 2s. This I am going to make it as y of s into, just cross multiply. So when you cross multiply you will get y of s into s cube plus 3s square plus 2s is equal to 10 u of s. So when you take a Laplace inverse, so if you wanted to convert your s domain to time domain, you will have to use a Laplace transform, inverse Laplace transform to convert your s domain to time domain. So when you convert you will get d cube y by dt cube. So after when you take a Laplace inverse for this particular equation, you will get d cube y by dt cube plus 3 d square y by dt square plus 2 dy by dt is equal to 10 u of t. That is, to convert your s domain to time domain you are going to utilize inverse Laplace transform. After this the equation can be written as y triple dot plus 3y double dot plus 2y dot is equal to 10u. Then by using a phase variable method. So phase variable method means the first variable will be your system variable. Here the system variable is nothing but your y. So x1 is equal to y. You consider the system variable to be the phase variable. Therefore x1 is equal to y, x2 is equal to y dot. The next state variables will be, the successive state variables will be the differentiation of your phase variables. So when you assume x1 is equal to y, automatically x2 x3 is going to be, x2 and x3 is going to be the differentiation of your assume phase variable. So here you will be getting dy by dt. x3 will be d square y divided by dt square. So you will be, once the state variable is written, always the state variables has to be represented using first order differential equation. So you need to identify what is your x1 dot, what is your x2 dot and what is your x3 dot. So x1 dot will be dy by dt. Also dy by dt is nothing but x2. So x1 dot is equal to x2. x2 dot is equal to d square y divided by dt square. So d square y divided by dt square is nothing but x3. x3 dot is equal to d cube y divided by dt cube. When you replace all your physical variable, so you have your physical variable over here. When all the physical variable has been replaced by means of your state variable, you are going to get the equation as stated here. It is x3 dot plus 3x3 plus 2x2 is equal to 10u. x3 dot is equal to minus 2x2 minus 3x3 plus 10u. So after substituting, you will get the state equation and output equation as shown over here, because x1 dot is equal to x2, x2 dot is equal to x3, and x3 dot can be written from this particular equation. After this is going to be your matrix A, and it is going to be your matrix B, and this is going to be your matrix C, and we are not going to do anything with the matrix C, and no need of this output equation. Why? Because to check for your controllability, I need only the matrix B and AB. Since the order of the matrix is going to be 3 cross 3, I have to use 3 terms in case of your controllability matrix. To find the controllability matrix, I will be getting 3 terms. First one is your B, second one AB, and third one is going to be your A square B. So, you know, B is available in this problem. AB means you have to multiply A and B. Next, A square B means this A matrix need to be multiplied twice, and then it has to be multiplied with the B matrix. After doing so, you are getting the controllability matrix as this one. And identify the determinant value for this controllability matrix. When you identify the determinant value, you got it is not equated, it is you have got minus 1000, which is not equal to 0. So when it is not equal to 0, then you can say the system is completely controllable and the rank of the matrix is equal to 3. Why here 3 in the sense? Because this particular problem have 3 state variable, therefore the rank of the matrix is going to be 3, and we can say the system is completely state controllable. Once the system is identified as completely state controllable, the next step is we need to identify the original characteristics polynomial equation with state feedback. Why? Because it is having a control law, u is equal to minus kx. So the characteristics polynomial equation representing the characteristics equation with state feedback is lambda I minus a plus bk is equal to 0. So we know the value of lambda I. I is your identity matrix whose order is equal to the order of the matrix A. Matrix A is identified in the problem, and B is also available in the problem. K is nothing but state feedback gain. Here 3 state variables are there, so we need to have 3 gains, that is K1, K2, K3. So how many state variables are available? Those many gain terms will be available here also. So after identifying the system controllability, as we discussed, you are going to identify what is your lambda I minus a plus bk. So lambda I minus a plus bk, you got this term. Identify the determinant value. So when you identify the determinant value, you got lambda cube plus 3 plus 10k cube lambda square. It means that the power of lambda cube, the constant associated with lambda cube is going to be 1, and the constant associated with the lambda square is going to be 3 plus 10k3, and the constant associated with lambda is going to be 2 plus 10k2, and constant associated with k1 is going to be 10. So k1 by default, from this only it is understood that k1 is going to be 10. So from this, once again, we need to obtain the desired characteristics equation from the poles. How many poles it is given in the problem? So in the given problem, 3 poles has been given. The first pole is going to be minus 2, second pole is going to be minus 1 plus j1, and the third pole is going to be minus 1 minus j1. When you multiply all these 3 poles for the desired characteristics equation, you will be getting lambda I minus ak. You will be getting the equation lambda cube plus 4 lambda square plus 6 lambda plus 4. Comparing this desired characteristics polynomial equation with the original characteristics polynomial, lambda square. So comparing the powers of lambda cube is not going to return any value of state feedback gain. Comparing the power of 2 for the lambda, you will get 3 plus 10k3 is equal to 4. So from this you can identify k3 is equal to 1 divided by 10. So the value of k3 is going to be 1 divided by 10. In the same way, you can compare the power of lambda between these two equations. When the power of lambda is compared between these two equations, you will get 2 plus 10k2 is equal to 6. So to identify the value of 10k2 is equal to 4 divided by 10, which is nothing but 0.4. So now you have already identified the value of k3 as 0.1 and the value of k2 is 0.4. Now comparing the constant coefficient between these two equations, that is, it is your desired characteristics polynomial equation and this is the characteristics polynomial equation with the feedback. When you compare the constant, you are going to get 10k1 is equal to 4, therefore k1 is equal to 0.4. So after solving, you got 3 gains, k1, k2, k3, which is k1 is going to be 0.4, k2 also we have obtained with 0.4, k3 as 0.1. So the 3 gains, state feedback gain k can be written as k1, k2, k3. So in this matrix, k1 is going to be 0.4, k2 is 0.4, k3 is 0.1. This is your state feedback gain for the given transfer function. So you people have obtained the state feedback gain and this is how you need to write it as a final result. Thank you students.